In the second part of the talk, we will mainly discuss the Fraser-Li conjecture in terms of the Weierstrass data. So this is the table of contents I will follow in this talk. So first, we will talk about sufficient condition for a surface to meet a sphere orthogonally. And second, Fraser-Li conjecture and Liouville equation as its equivalent form will be mentioned. So lastly, we will discuss what we can deduce regarding the conjecture in terms of the Weierstrass data. So results in this talk are from joint work with Jeon-Li. So the Fraser-Li conjecture asks that if the critical catenoid would be the only embedded free boundary minimal annulus in B3. There are some results regarding this conjecture throughout the years, so I will state them. So this conjecture is actually an old conjecture which goes back to Nietzsche's result in 1985. So Nietzsche showed that free boundary minimal disk in B3 must be an equatorial disk. And Ross and Soam in 1997 generalized Nietzsche's result to space forms, and Fraser and Shane generalized Nietzsche's result to the higher dimensional ball. So disk type free boundary minimal surface in Bn must be a planar one. And recently, McGrath showed that embedded free boundary minimal annulus in B3 symmetric to 3 coordinate planes, then it must be critical catenoid. So only partial results are known for now for this conjecture. So we now talk about sufficient condition for a surface to meet a sphere orthogonally. From previous talks, we already know that by Theorem-Joachimsthal's theorem, if surface sigma in R3 meets the unisphere S2 orthogonally along gamma, then gamma must be a line of curvature. So this theorem tells this fact. And geodesic curvature along gamma computed on sigma must be equal to 1. But we could ask that if these two conditions are sufficient condition for a surface to actually meet a sphere orthogonally. So we can find out that this converse is also true. At first glance, the free boundary condition can be considered very powerful, so it could tell us more. But it turns out that it's not the case. So actually, the following classical result can be used to show that those two conditions are sufficient conditions for the surface to meet a sphere orthogonally. This criterion is very famous result, a famous well-known fact. And we see that these terms here are expressed in terms involving curvature and torsions. And this is a necessary and sufficient condition for a space curve in R3 to lie on a sphere. And actually, by simple calculation, we have following lemmas. So lemma 1 tells us that if gamma is a line of curvature on a surface sigma with constant geodesic curvature c. Moreover, if gamma has a non-vanishing torsion as a curve in R3 and does not contain any oblique points, then there exists a sphere of radius 1 over absolute value of C such that it intersects sigma orthogonally along gamma. And along this lemma 1, we can also get the lemma 2, and it says that if gamma is a line of curvature on the surface sigma with the constant geodesic curvature C, which does not contain any oblique points. So in this case, if the torsion of the gamma is identically 0, then gamma is a part of a circle. So in this case, therefore sigma is orthogonal to a sphere of radius 1 over absolute value of C on gamma. So basically, these two lemmas tells us that indeed two conditions are sufficient condition for the surface to meet a sphere orthogonally. So after these lemmas, we get this proposition. So this proposition tells us the two conditions. One is gamma being a line of curvature, and the other one, gamma having constant geodesic curvature, imply that the surface must meet certain sphere orthogonally. Maybe we imposed some conditions such as gamma should be real analytic and gamma having finitely many oblique points, but we are mainly talking about minimal surfaces anyway, so they obviously satisfy those conditions if gamma lies on the interior of the surface. So we was able to get this proposition. We move on to the second part. Here we talk about the relation between the Fraser-Li conjecture and a certain type of Liouville equation. We observe that the following Liouville type boundary value problem is related to the Fraser-Li conjecture. So we denote this boundary value problem E R epsilon C0. So to see what these equations represent, we have to see the following. So it goes like this. If we have a free boundary minimal annulus, then we have a minimal immersion from this annulus to R3. Then we are planning to impose condition that the surface has real analytic boundary, so we can extend this immersion to slightly larger annulus like this, A1 minus epsilon and R plus epsilon. So we get a extended immersion here. And then using a half differential, one can show that the second fundamental form is given by this form. And then after calculation, we get this equation here. And using Simon's identity, we get an equation here. And then after calculation, we get an equation here. So as a result, we can put v as a function log 1 over r to the 4 and lambda squared. And here lambda is a metric vector given by lambda squared, dz squared equals the metric. So if we consider this v here, then we see that this by Simon's identity, this v satisfies this first equation, the Liouville equation. So this first equation comes from the v here, and second and the third equation here obviously implies that the surface has so a boundary of the surface has constant geodesic curvature. And last equation here comes from the fact that the boundary length of the boundary of the surface and uh, and area of the surface has the relation like this. So if we write it, then it goes like this. So twice the area equals the length of the boundary. It comes from the free boundary condition. So we have this boundary value problem, and we are curious that if this or if we find a solution to the boundary value problem as this, then would we have a free boundary minimal annulus as well? So that's the theorem here. So this theorem tells us that if V is a solution to the previous boundary value problem, then there exists a minimal immersion X from an annulus to R3 and a unit sphere where they intersect orthogonally along lever curves z absolute value of z equals 1 and absolute value of z equals r. So moreover, the solution V satisfies this equation we saw earlier, where lambda is a metric vector induced by x. So basically, we can say that solving this boundary value problem and finding a free boundary minimal annulus is a same thing, really. So the proof of the theorem basically is going backward, the things that we talked about. So we will introduce the proof in a brief manner in the next slide. So the sketch of the proof goes like this. So by applying the same method in Jimenez's paper, we see that the solution V can be given by the form like this. So here H is a some locally univalent meromorphic function defined in an annulus. So we write H like this, and then let us consider a minimal immersion X. Defined by the Weierstrass data. So we can put the Weierstrass data as follows. Then we will prove that X is indeed is well-defined immersion with no real period. First, we can look at the metric vector here. So lambda can be calculated by the Weierstrass data as follows. So after some calculation, then we see that lambda squared is can be expressed in terms with h here. So we obtain that v equals this as before. So with this um, with this equation, we see that second and third equations of E r epsilon c0, the geodesic curvature of lever curves z absolute value z equals 1 and absolute value z equals r has constant geodesic curvature. Moreover, the second fundamental form can be given as with the advisors data like this. So we instantly see that the lever curve z, so z absolute value of z equals constant is a line of curvature of the minimum surface. So we now are able to apply proposition we talked about, but we have to be careful for one thing, because as we can say that there is a sphere per one boundary, and we have two boundaries here. So there could be two spheres like this, and surface can be like this, so that we have to exclude this case for sure. But this case here can be excluded by the next lemma we will present. So we are now left to show that X has no real period indeed. So let us assume that this minimum surface in this immersion has real period. Then we can consider the minimum surface corresponding to the triple of the period. And we know that this lever curve here must lie on the sphere by the proposition we talked about earlier. But at the same time, because we are considering the minimum surface of triple of the period, there are three collinear points that are that must lie on the sphere, which is nonsense. So we find out that this immersion cannot have real period. So we are done with the proof here. So the next lemma actually says that there cannot be two spheres with different centers, O1 and O2, respectively, such that each SOK, this denotes the sphere, intersects sigma orthogonally along two boundaries, lambda k here. Recall that this condition here was the fourth line of the boundary value problem we presented a few slides ago. So we find out that these two different sphere cases cannot exist in our settings. So this lemma completes the proof of the theorem. So we conclude this second part with this mark. So since the rotationally symmetric free boundary minimal annulus in a ball is known to be the critical catenoid, it follows from theorem that solving the Fraser-Li conjecture in real analytic boundaries is equivalent to showing that the solution of E r epsilon c0 has a radial symmetry whenever it exists. So we are proposing a new approach to the Fraser-Li conjecture, And maybe attacking the Liouville type PDE problem will give us some of the facts that we were not able to get. So this might be a new approach to the problem. So we will wrap up this part and move on to the third part. We will now talk about Weierstrass data and the Fraser-Li conjecture. So what we know so far, we can consider this Fraser-Li conjecture in terms of Weierstrass data as follows. So we can parameterize the free boundary minimal annulus in a concentric annulus here. So we get this immersion from an annulus A to sigma, and we denote this immersion by X. And we know that concentric circles in A is lines of curvature. So we know that this surface sigma is foliated by the line of curvature. And then the catenoid, real critical catenoid, has the property that set of line of curvatures are same as the set with the coordinate function x3 being constant. And it's also same with the set that the radius of the Gauss map being constant. So if we can show either of two sets are same for our case, then we can actually show the uniqueness of the problem. But it's not easy at all. But we were able to show the following fact. So this is a proposition 2, and the Gauss map G from an annulus A to C must be an one-to-one map, and the image of the Gauss map GA is a doubly connected domain in C bounded by two closed curves GCI. So with this proposition, we can say more things at the above. So we can also define a Gauss map G to get a doubly connected domain, which is bounded by GCIs. If we denote this two curves C1 and C2, then since we can always see this Gauss map G as a holomorphic function, and being this map one-to-one, then we can also parameterize the surface with this Gauss map here. And to be exact, we can parameterize the surface with the inverse of the Gauss map. So being able to parameterize the surface with the inverse of the Gauss map, we can actually use the Weierstrass data in more easy manner, because the calculation gets much more simpler with this parameterization. So we were thinking that this proposition here, by the way, this is not an obvious fact at all, and this proposition can be used to get some results on the conjecture. we were especially trying to show the uniqueness of the surface under one or two symmetric planes. Setting a symmetric planes, we can get symmetric behavior of the Gauss map and actually of the line of curvature. So we can say a lot of things in terms of Weierstrass data, but actually we could not get any uniqueness result under the symmetry, so it was kind of disappointing. And this proposition so couldn't go into any other paper. Um, so I have to say that this Weierstrass data method has its limitations. So I will finish this talk with this remark. So it seems that this holomorphic method using Weierstrass data has its limitations to get appropriate results concerning the Fraser-Li conjecture. And it's probably because this Weierstrass data are observing only local properties, mainly local properties, and we have to deal with this boundary conditions, and it is not a good method when dealing with, especially dealing with two boundaries here. So I think it has its limitations. So at first it was hopeful, but we couldn't get any other result using Weierstrass data. Strange thing is that we couldn't get the result with the condition that the surface is symmetric to three coordinate planes. Yet it was actually proved by McGrath a few years ago. So we used every condition that we could do, and we actually know that this being line of curvature and having constant geodesic curvature is sufficient condition for the surface to be free boundary. But anyways, we were not able to get uniqueness result out of this. But anyways, we wanted to introduce the above proposition because as itself, it's a very interesting fact that the Gauss map is actually an one-to-one map. So it might help other mathematicians to attack the problem. So, okay, so I will finish my talk here, and I want to thank all the audiences watching this video, and want to again thank Fraser-Li doing all this work to hold this event, and thank you again.